something that's fair and that you can solve. No tricks, no trick questions. That reminds me, a few years back, I was trying to be cute in an exam, and the last question was, for 5 points, write your own question and then answer it. And the best answer will be read out loud in class. That was a complete disaster. People thought it was a trick question, and they tried to do something very sophisticated. They could have just said, what is methane, and then write CH4, right? So after 30 minutes of grading, the TA sent me a delegation and said, this is a complete loser, okay? They're going all over the place with this. So I looked at some of these exams and said, okay, give everybody 5 points, but still find the best answer. So they looked through all this stuff, and then they came back to me, and I had to read this out in class. And the best answer was, the solution was, question, if Volhard and his teaching assistants were to be thrown out of an airplane, who would hit the ground first? And the answer was, who cares? Passed it. All right, let's have a break. Okay, so one other thing I forgot to mention, knowing what's to come. You can and you should plan your strategy on which problem to tackle first. Since you know what's there, you can now say, okay, I'm going to do question 3 first. If you're good in synthesis, that one first, or multiple choice first. The reason I'm saying this is take your best question first, because it'll settle you down, all the nervousness and excitement. The fact that you have, put away 40 points there in your pocket has a very calming effect on people who take exams, obviously, right? And it also avoids you running out of time, such that at the very end you realize, oh, I knew how to do that, but I didn't have enough time to do it. Okay, that's out. You can really plan you can even time yourself on the practice exam, so you know exactly how long it's going to take you. Okay? So that's strategy. Okay, so let's move on now to the next chapter, which deals with one of the, perhaps maybe the most important functional group in organic chemistry, and that's the CO double bond. And the one that we'll talk about today, and in the next chapter, will be the carbonyl function as it exists in aldehyde and ketones. Aldehydes are the carbonyl compound in which one end is capped off with a hydrogen, and the alkyl group is on the other end. And ketones have 2 alkyl groups. So here's a molecular model, and as you already, some of this is just review. We've seen that before. It's just now all summarized in one chapter. The CO double bond is like an alkene double bond, except that one end is an oxygen. And there are no substituents, but rather lone pairs on that carbon. So the pi bond is just a normal pi bond. The oxygen is sp2 hybridized, and there are in 2 sp2 hybrids that are perpendicular to the singly filled orbital that makes the pi bond. There are 2 electron pairs, the lone pairs. Okay? So in case you didn't know where these lone pairs sit, when we draw these dots on a carbonyl, they're sitting here, okay, perpendicular to the pi frame. And we shall see that these guys can be protonated, so they're somewhat basic, and that the CO bond is polarized, which determines the entire reactivity of the carbonyl function. There's 2 chapters after that will be carboxylic acids, which is the carbonyl function where we have an OH or X instead of an H. That's another 2 chapters. So there are 4 chapters devoted to carbonyl chemistry. Nomenclature-wise, this is the first time where we actually have to dig in a little bit into priorities. Priority rules are such that alkanes and haloalkanes and substituted alkanes are lowest on the totem pole. Then all the other hydrocarbons, okay, the enes, the ines, and the benzenes. Then alcohols. Alcohols so far actually were the highest priority functions. That's why benzenol is a benzenol and not a hydroxybenzene. We mentioned that very recently. And now we're introducing the carbonyl. And the carbonyls are actually higher than anything else we've seen so far. So we're adding something on top of the totem pole. And within the subgroups of aldehyde and ketone, aldehyde has precedence over ketone. So in our hierarchy, it's now aldehydes, then ketones, then alcohols, and then all the rest. So we are using systematic naming. So aldehydes are very simply derived from alkanes by changing the ending E to al. Okay? So hexane turns into hexanal. The longest chain starts at the carbonyl carbon because by default, and this makes things very easy for aldehydes, the functional group has to be at the end. If it's not at the end, then it's actually a ketone. So the fact that you have a hydrogen on one side of the carbonyl means that that is the beginning of the chain. And since it's a function, it's the beginning of the longest chain. You just have to find where the longest chain is. So if you have a chain with branches, you have to follow up and down until you find that chain that is the longest, and then everything else is the substituent to that longest chain. But that's where the chain starts, and therefore this carbon is C1. So there's some quirks here. The IUPAC calls these alkanals, but nevertheless, it decided that these guys, the 2 smallest ones, are so common that the common names are accepted. So instead of methanol, we call this guy formaldehyde, and instead of ethanol, we call this guy acetaldehyde, and we've used those terms before. After that, once you get to 3 carbons, it's straightforward alkanal. So this is propanal, this is a butanal, this is 7 carbons, this is a heptanal. And once you put substituents in, then it's just straightforward. After you number down the chain, this one has a 4-chloro, so it's 4-chlorobutanal. This one has a 4-methyl and a 6-methyl, so it's 4,6-dimethyl heptanal. So that's actually quite straightforward. Cyclic aldehydes have a little quirk. You call them you use cycloalkane nomenclature, and then add, if it's an aldehyde, add the end in carbaldehyde. Okay? And now the carbon attached to this CHO group, which is called formyl, is carbon 1, not the carbon of the formyl group because of the cyclic system. So this is carbon 1. And this, for example, would be called cyclohexane carbaldehyde. This is a little bit of a monkey wrench. I was elected years ago to the IUPAC committee in nomenclature, and I served for 8 years. And it consisted of meeting once a year in some exotic resort in the Mediterranean, like Nice or Cannes or Acapulco in Mexico. And we would sit around the bar and drink cocktails and come up with these rules. And that's why some of them are shaky. So here you go. So you got to remember that this is carbon 1, and this guy is basically dangling. So this is a cycloalkane carbaldehyde, cyclohexane carbaldehyde. So otherwise, once you have that straight, then it's okay to just number around the ring, give the next substituent the lowest locum. So this guy, for example, has an ethynyl group at position 2, and you see the stereochemistry. So this is cis. So this is cis 2-ethynyl cyclohexane carbaldehyde. And if I wanted you to indicate the absolute stereochemistry, you would have to assign RNS nomenclature designators to these 2 positions. Here is a benzene carbonaldehyde, so this applies to benzene, and this is also carbon 1. Okay, so this would be 3-methoxy-4-hydroxy. Now remember, this is 4-hydroxy because the aldehyde has precedence over alcohol. So this is no longer a benzenol, it's a benzene carbonaldehyde. And 4-hydroxy and then 3-methoxy. There's another quirk that shows up here. Notice 4 is before 3 because in the naming we follow the alphabetical ordering ever since chapter 2. And so the numbers follow the alphabetical ordering. So it's not numerical ordering, it's alphabetical ordering. So since H is before M, the 4, because the hydroxy is at 4, comes before the 3. And as I just mentioned, that unit here as a substituent, which will become significant when we have higher priority functional groups like carboxylic acids, is called formyl. Or something, just colloquially, you refer to this unit as formyl. Now ketones are reasonably straightforward. That's alkanes turn into alkanones. And indeed, it's very much the same as alcohol nomenclature. You number the longest chain containing the carbonyl function from the end that's closest to the function, like in alcohols. So in this case, for example, this is a pentane-derived ketone, so it's a pentanone, and the carbonyl is at position 2, which is closest to this end here, so that's why it's 2. So you don't number from here. Cyclic ketones are simply called cycloalkanones, and now, fortunately, logically, the carbonyl carbon is carbon 1. So one more example here. This is a heptane-derived ketone, so it's a heptanone. The one is at carbon 3 because you number from the right, and so that puts chlorine at 4 and methyl at 6. So it's 4-chloro, 6-methyl, 3-heptanone. Here, C is before M, and this coincides with the numerical ordering. But that is purely coincidental. Okay? It's dictated by the alphabetical ordering. And so this would be a cycloalkanone, a cyclopentanone, position 2, and this is carbon 1. Position 2 is 2 methyls. Oops. So then we can have the interesting situation where we have both an aldehyde, a formyl function, and the carbonyl function of a ketone in the same molecule. And as we learned, and that's why the rule was invented, aldehydes have priority over ketones. So those guys are always called alls, alkanals. And the position of the ketone carbonyl is designated oxo, with a prefix number that indicates which carbon has the CO double bond. So these are essentially then called oxoalkanals. Here's an example. This is a 4-carbon aldehyde, so it's a butanal, but it's got another carbonyl function at carbon 3, since this is carbon 1, so it's 3-oxobutanol. Okay? Sort of like 3-hydroxy if it were an OH, but in order to indicate it's a CO double bond, it's called 3-oxo. As a substituent name, the RCO function is called acyl. And when you know the length of the alkane chain, it's alkanoil. So 3-carbon piece with a carbonyl at the end is propanoil. And we've seen that naming in the alkanoil halide naming of the Friedel-Crafts reagents, where we have CO chloride. So there's a propanoil chloride and butanoil chloride. And again, the smaller ones have common names. We already did this for H here, that was formal. For the smallest ketone-derived, acyl-derived species, the acetyl is allowed. So this is the same reason why acetone is allowed and acetic acid is allowed and so on. It's UPAC accepted these common names because they're all over the place. But after that, UPAC stipulates systematic naming. So it's alkanoil, so with 3 carbons it's propanoil, 4 carbons butanoil, and so on. So what about the structure? We already had some hint of that looking at the model. And the bottom line is it's a CO double bond is polarized. So you can view it like a CC double bond, but one of the carbons is now an oxygen. Oxygen, as you know from the periodic table, more electronegative than carbon, it pulls. It pulls quite well on a single bond, but now with the double bond, the pi portion of the double bond is rather soft. These electrons are not as tightly held around the nucleus. They're deformable. So the polarization induced by the electronegativity of oxygen is even more pronounced, such that we have a strong delta plus here, as indicated here, and a strong delta minus here. And that's often written by writing the dipolar resonance form, where you have a full negative charge of oxygen, which shows you that this oxygen can be nucleophilic and basic. Primarily, we'll see this as a protonation. But by far, the more important aspect will be that nucleophiles will attack this carbon, which is electrophilic. And that governs the next 4 chapters. Nucleophilic addition to that carbonyl carbon. And in fact, this is not something that's totally new. We've already used that in chapter 8 when we added Grignards in alkyl lithiums. R- equivalents, strong nucleophiles, to the carbonyl carbon. The electrostatic potential map shows that too. Notice the strongly blue nature of that carbon. If this oxygen weren't there, but it were a carbon, like in ethylene or ethene, in an alkene bond, that carbon would also be red. Both of them would be red. But because of this polarization, the carbonyl carbon is blue. And if you look at the structure, it's sp2 hybridized at that carbon, as you would expect. There's a slight reduction of this 120-degree bond angle by about 6 degrees. And this is because these oxygens, these electron pairs, that are now no longer bonding electron pairs because there's no substituent. They're closer to the oxygen, pushing a lot of electron density here and here, and that pushes on the electron density of these bonds here, making them bend back a little bit. Okay? So it all pans out very nicely. Not much, but 6 degrees is noticeable. But otherwise, the structure is just as you expected. And the essence is, looking at the orbital picture here, which reflects the model, oxygen is sp2 hybridized. There's a p orbital that makes the pi bond, and there are 2 orbitals, sp2 hybridization that indicates that these electron pairs are perpendicular to the pi bond and can be approached by usually proton or other electrons. We'll do more of this next week. Have a nice weekend.